Welcome to Hewlett-Packard, Corvallis, Oregon. This is where the HP-48 was conceived, designed, prototyped, tested, and first manufactured. Right now, there are about 1,000 people here working in calculator manufacturing. Hello, I'm Bill Wickes. I was the project manager for the HP-48's built-in software. That's the programs that makes the calculator work. Everything from recording key presses to making the clock tick in the display, from computing sines and cosines to taking a derivative or plotting a graph. This is where I work. It's a typical R&D person's work area. Everyone in the area nearby here worked on the HP-48, software, mechanical design, and electronics. All the clutter you see around here is related somehow to calculator development. In a few moments, my colleague Nathan Meyers, who was also part of the HP-48 development team, is going to take you on a how-to tour of the HP-48 and its problem-solving capabilities. Before you meet Nathan, I'd like to tell you a little about where the HP-48 came from and what we had in mind when we developed it. People like me have been developing scientific and business calculators here at HP since 1972. The product that started the whole business was the HP-35, which amazed people back then by calculating trig functions and the like at the press of a key. The 35 contained about 750 bytes of pre-programmed memory and sold for $395. Today, for $45 less, you can buy an HP-48SX, which has over 300 times as much memory. You can see that we've been making great strides in hardware as well as in software. Part of our HP calculator tradition is for each new product to build upon the successes and learn from the shortcomings of its predecessors. The HP-48 traces its roots all the way back to the HP-35. You can see the same double-wide enter key that has been on every HP scientific calculator. The 48's most immediate ancestors were the HP-41 and the HP-28. The HP-41, introduced in 1979, combined the best yet computational functions with a remarkable hardware flexibility that allowed you to add new software and connect additional devices like printers. This lets you create your own personalized calculator, set up to run just as you want. That concept was so successful and popular that the HP-41 sold for more than 10 years, quite remarkable in today's fast-paced world of electronics. When we designed the HP-28, we wanted to take the 41's best calculation capabilities and generalize them to apply to a wider class of math problems than the HP-41 addressed. We also wanted a calculator that you could learn with and learn from and use as a mathematical exploration and modeling tool. Thus, the HP-28 became the world's first calculator that could deal with symbolic calculations, algebra, and calculus. It incorporated complex numbers and matrices into the same flexible interface that the HP-41 provided for ordinary numbers. The HP-28 is a very successful product too, but it doesn't have the customizability of the HP-41. That's where the HP-48 comes in. It combines the HP-41's flexibility, plug-in software, communications, and keyboard customizing with the advanced computation technology of the HP-28. We listened to every criticism of the 41 and the 28 and every request for enhancements and designed the HP-48 from what we learned. When you watch Nathan in a few minutes, don't let the 48's large number of functions and features bother you. The 48 is designed so that all of its operations work pretty much the same way. The secret to learning the HP-48 is to focus on one particular problem. Once you learn how to solve that problem, you'll find that the same style and methods that you learned apply to every other problem that you might attack. You don't have to start from scratch for each new problem. Consistency and uniformity were our highest objectives in the design of the HP-48. I'd like to give you a brief illustration of how the 48 is designed to work the way you think. When you use it, you'll find that you never have to write anything down or retype anything. This is because the result of any calculation is always immediately ready for additional calculations. Let me show you what I mean. Suppose I want to add two numbers. Here's how I would do it on paper. First, write the numbers down like this. Then, add them. Notice two things. First, I wrote the numbers before I added them. In fact, after I wrote them down, I could have even changed my mind and subtracted or multiplied instead. Second, the result is ready for additional operations. I could now write down another number and add it to the total. This is exactly how the HP48 works. It's not the way most other calculators work, but it is the way you have done arithmetic ever since you were in grade school, so it certainly isn't hard to learn. Well, enough introduction. I'd like to bring Nathan on now to get down to business and show you how to use your HP48. Thanks for listening, and enjoy your calculator.
Hi, we're going to introduce you to the HP48 calculator from Hewlett-Packard. It just may be the most powerful scientific calculator on the market today, and it gives you new ways to solve problems too. In this video, we'll show you how you can start using the 48 for solving different kinds of problems. This video has 12 segments. They're listed on the case. Each one covers a separate topic, but builds on the earlier segments. So we suggest you watch them in order, at least the first time. Later, if you want, you can skip to any segment. To help you find a certain segment, each one's marked with a number, what we call the video index, here in the lower left corner of the screen. Let's get started by turning on the calculator and trying a few things. The calculator we're using is just as it comes from the factory. Memory's clear, and everything's in its default state. Whenever we show the 48, we'll show the display off to one side. This lets us zoom in a little closer. You probably guessed it. The on key down here turns on the calculator. You can check the display to see if it's too light or too dark. If you want, you can adjust it by holding the on key down, then pressing the plus or minus key, like this. Okay, here's a simple calculation, multiplying two numbers and adding a third. It'll show the 48's RPN style of calculation. Press 1, 4, then press enter. This saves the 14 and lets you start the 38, 3, 8. Then press times to multiply the two numbers. You see the result in the display. It's ready for the next operation. Now press 1, 5 plus to add 15 to the old result. The answer is 547. So to use a command with RPN, you enter the numbers first, then do the command. This is true for all commands. Enter all information for the command, then do the command. The command takes away the numbers it needs and puts back the results. The results are ready for the next command. Suppose you want to square this answer. The number's already there, so just do the square command. It's the orange x squared label above the square root key. Press the orange left shift key, then the key under the x squared label, like this. That's 547 squared. Since we won't need this result anymore, press the back arrow key to delete it. Okay, let's do another calculation. It'll show us some more about the 48. Let's figure the budget for a building foundation. The design calls for 90 yards of concrete and 4,800 feet of rebar. Concrete costs $46 a cubic yard, and rebar costs 35 cents a foot. The cost for concrete is $46 times the number of yards, 90, so 46 enter, 90 times. The cost for rebar is 35 cents times the number of feet, 4,800. 0.35 enter, 4,800. Before we press times, notice something. See how the numbers we calculated or entered moved up on the display as we entered other numbers. They're in the calculator's stack, part of the calculator's memory. The rebar cost per foot's in level 1. The total concrete cost's in level 2. There's nothing in level 3, not even a 0. And the number we're entering isn't on the stack at all. It's in the command line. The command line shows up whenever you enter data. You can correct the number you're entering before using it, like backspacing with the back arrow key. The number doesn't go on the stack until you press enter or do a command that uses the number, like times. So now press times. See the two costs in the display? They're ready to add, so just press plus. The expected cost is $5,820. We'd better add a little extra for emergencies, say 15%. The calculator has a percent function, but it's not on the keyboard. It's in the math menu. Press the math key, here. Look at the menu labels at the bottom of the display. Each label matches a white menu key below. The small bar at the top of a label means it gives another menu. The percent function's in the parts menu, so press the menu key below the parts label. The percent function still doesn't show. It's on the second page of the menu. So press the next key, here. Okay, there's the percent label. Now we're ready to find 15% of the cost. First, we need to make a copy of the cost. The percent function will take a cost number for its calculation. There's no command line right now, so just press Enter to make a copy. Then press 15 and press the percent menu key. That's 15% of the cost. Now we can add the two numbers, plus. The budget is $6,693. You can do a lot more with your calculator than just crunch numbers, so you'll need to know how to type letters and other symbols. Let's see how. A simple string of text is marked by quote marks. If you don't use quotes, the calculator might think you're typing a command. So start with right-shift quotes. You get the start and end quotes in the command line, and the cursor is between them. You're ready to type. Use the alpha keys to type text. See the white letters to the right of these keys? They're some of the alpha keys. One way to type a letter is by pressing the alpha key, here. See the alpha symbol in the display? Then the letter key, like H. Do it again for the next letter, alpha P. Here's the space key. And you can type numbers too, like 48. When you're done, press Enter to put the text string on the stack. See, the text string goes on the stack just like the numbers did before. If you're going to type a lot of text, you don't have to keep pressing alpha for each letter. You can hold the alpha key down while you're typing, then let it up when you're done. Or you can press alpha twice, and the alpha symbol locks on until you press it again. That's what we'll do in this tape so you can see the calculator better. The left and right shift keys give more alpha characters, but they're not shown on the keyboard. You can find them in the owner's manual and on the back of the quick reference guide. Okay, let's try another text string. Right shift quotes, alpha alpha. Then type lowercase is, uppercase great, and exclamation. Space, left shift I, left shift S, space, G, R, E, A, T, left shift delete for the exclamation mark. Then press alpha again to turn off the alpha keyboard. Now, it doesn't make much sense to do arithmetic with text strings, but it may seem logical to add one string to another. And that's what happens if you press plus. You can add numbers, and you can add text strings. Soon you'll see that the 48 can work logically with several kinds of data, several kinds of objects. Earlier, we used the percent function. Remember? It showed up in a menu. Well, the calculator has lots of menus. They have all the functions that can't fit on the keyboard. These four keys get the math, programming, custom, and variable menus. We used the math menu earlier. If you look closely at the keyboard, you'll see that some of the orange labels are on darker backgrounds. They're menus too. So, left shift modes gets a menu for setting operating modes. Keep your eyes on the menu labels for the next few steps. Left shift modes. Most menus have right shift versions too, even though there's no blue label. Right shift modes gets a different menu. But let's go back to the first modes menu, left shift modes. This menu has 4 pages. Press Next to go forward through the pages. Press left shift previous to go backwards. Some labels have a small box to show that a condition is true, like degrees mode here. If you press radians to set radians mode, the box moves to the radians label, and the radians enunciator comes on. To get to a menu, you usually have to start by pressing one of the main keyboard keys. There's no way to back up in the menu structure. But if you want to go back to the last menu you used, you can press right shift last menu. That's the last menu we used. So, menus give you an easy way to execute commands. You don't have to remember the exact spelling. You just go to the menu and press the key. We'll be using lots of menus later, but if you want, you can always execute a command by typing it in the command line. For instance, you can get back to degrees mode by typing the degrees command. You can lock alpha for this, alpha alpha, then watch the radians enunciator turn off. D, E, G, enter. Before we finish this introduction, there's one important key you should know about, the attention key. Actually, it's the on key, but it's also marked attention. If you press this key, it cancels whatever you're doing. If you're typing a command, attention wipes out the command line. If you're running a program, it stops the program. If you're making a plot, it puts you back at the stack display. It also clears error messages. It's pretty handy for getting back to a familiar place. Before turning off the calculator, let's see how you clear the stack. It's a good idea to keep it uncluttered. Things work faster that way. Use the clear command here. Press right shift clear. To turn off the calculator, press right shift off. It's above the on key. Right shift off. The calculator turns itself off after 10 minutes of inactivity. Well, we saw a few things about the 48 in this segment. If we went a little too fast, you could rewind the tape and watch it again. But we'll be using these ideas again later, so you'll have a chance to see them again. Enjoy your tour of the HP 48. Probably the main reason you have a 48 is to help you solve problems. Well, it's a pretty versatile tool for doing just that. In this segment, we'll talk about 6 ways to solve different types of problems. In general, problems have similarities. There's usually information you know and information you want to find, and you need a way to turn the known information into the answer. But the type of known information and the type of answer you want may vary a lot from one problem to the next. So the process you use depends on the problem. In the next few examples, we'll see only parts of calculations. They'll show different methods for solving problems. For simple problems, and ones you don't need to repeat often, you can use simple numeric math. We did that earlier when we found the cost of the foundation. So you can get the negative square root of 3 like this, square root of x plus minus. For problems that require symbolic solutions rather than strictly numeric results like an algebra class, or for numeric problems you may want to solve many times for different conditions, you can use symbolic math. Doing algebra on a calculator may be new to you, but you can do it. Solve this equation for m, tick, alpha m, isolate. For numeric problems that you'll resolve many times, or with different unknown parameters, or that have complicated relationships, you can use the HP Solve application. The numeric solver lets you quickly try different combinations of known and unknown parameters. For given values of f and m, solve for a, 30f, 4m, left shift a. For problems where you want to see a function's behavior so you can pick out the answer you want, then get a numeric solution, you can use the plot application. You can also plot polar functions, parametric equations, conic sections, even statistical data. Find the middle root of this function, left arrow, root. For problems where you want to just enter data and calculate a result, and you want to do this more than once, you can make a user-defined function. Use the user-defined perimeter function to get the perimeter of a 100 by 50 foot field. 100 space 50 perimeter. For problems that are more complicated than the previous kinds, you can make a program. If the answer has several parts, if the problem needs complicated logic or repetition, if you want special prompting or special output formatting, you can make a program. Almost anything you can do on the calculator, you can do in a program. Use this program to get the positive and negative square roots of the number on the stack. Evaluate. So you have at least 6 ways to solve problems, and as you learn more about them, you'll probably find ways to combine them for even more flexibility. But before we go any further with problem solving, we should look at a couple of important ideas. Don't worry about the details now, they'll show up again later in the tape. For now, just focus on the general concepts. In the first segment, we did calculations with numbers, and we did some work with text strings. Well, numbers and text strings are just 2 examples of objects. Objects are the basic elements of information the calculator can handle. Numbers and strings are 2 examples. Well, the 48 handles 20 kinds of objects. Maybe this seems like a lot of types, but just about everything the calculator does, and it does a lot, it does with objects. So if you know about the different kinds of objects, it'll help you learn to use the 48. This list shows some typical kinds of objects. We'll use most of them during this tape. The first several types represent different kinds of data, real and complex numbers, text strings, arrays of numbers. A unit object is a number that has measurement units attached. It's more than just a simple number. Programs and algebraic objects are different ways of showing sequential behavior, much like you'd think of a program. Think of program and algebraic objects as procedures you'll execute. Think of a list as just a collection of objects, without the idea of execution. A built-in command is just another type of program. A name object lets you use a name to represent any other object, like a mathematical variable. Now, each kind of object has a standard format that shows what kind of object it is. Remember the text strings and the quote marks? Text without quote marks would be mistaken for numbers, commands, or names. Different kinds of delimiters identify different kinds of objects: parentheses, quote marks, brackets, underscores, French quote marks, tick marks, and braces. The delimiters make it possible to show different kinds of objects at the same time. You don't need a program mode or alpha mode to see certain kinds of objects. Even though there are many kinds of objects, the calculator treats them consistently. You store them the same way, you recall them the same way. If you recall an object, it takes up one level on the stack, regardless of its complexity. So, for example, level 1 of the stack can contain something as simple as a number, or something as complex as a large, complicated program. And commands adapt to the objects you're using, as much as possible. Remember how we added numbers earlier, and added text strings? You can also add arrays, and algebraic objects, and lists. This gives you some pretty versatile tools to work with many kinds of data. The important thing to remember is that the calculator works with objects, and different objects are just different kinds of information marked in a way that identifies their nature. In this segment, we've seen a few ways to solve problems, and we've seen some of the kinds of objects you'll use while solving them. In the next few segments of this tape, we'll look at each of the problem-solving methods. You'll see how handy they are for different kinds of problems. After that, we'll look at a few other things about the 48, features that give you even more flexibility, more convenience. So now we're ready to start solving problems. You're probably familiar with the idea of using a calculator to do numeric calculations, what we call numeric math. You enter numbers, do some math operations, and get numeric answers. In this segment, we'll find out a few more things about the stack and command line, about doing math, and about how numbers are displayed. The calculator stack is the area of memory where most commands operate. You can see the first few levels of the stack in the display most of the time. Level 1 is sometimes called X, and Level 2 is sometimes called Y. This lets you understand some of the math keys, like square root of X and Y to the X. In this discussion, we'll talk mostly about numbers on the stack, since we're talking about numeric math. But remember, the stack works the same regardless of what kinds of objects it contains. One way to put numbers on the stack is to enter them from the keyboard. As you enter other numbers, previous numbers move up into higher levels. 6, enter. 7, enter. As you use commands, they remove numbers from the stack and put results back on the stack. Times. The size of the stack changes according to how many objects are put there. It can have no entries, it can have 1 or 2 entries, or it can have hundreds of entries, depending on how much memory is available. This is quite different from earlier HP calculators, like the HP41, that always had exactly 4 numbers in its stack, X, Y, Z, and T. With the 48, you can have as much information available on the stack as you need, and when you clear the stack, you have no information there. If there's not enough data on the stack for a command, you get an error. So if you clear the stack, enter only one number and press plus, you get an error. Let's find the area of the walls and ceiling of a room that's 14.4 feet square and 7.8 feet high. The area consists of 4 equal rectangular walls and a square ceiling. First, enter the dimensions, 14.4, enter, and 7.8, enter. In this example, we'll enter the dimensions only once. If the numbers aren't in the right position for the next command, you can move the numbers around. Certain commands simply change the arrangement of numbers on the stack. You can see some of them in the Stack menu. Press Program, then Stack. For this problem, you need the wall length for the wall area and for the ceiling area. Right now, it's only in Level 2. Well, the Over command creates a copy of the number in Level 2 and adds it to the stack at Level 1. Now there's 2 length values. Press times to multiply the length and height. That's the area of the wall. Multiply by 4 to get the total wall area, 4 times. Now you need to get the length into Level 1 so you can find the ceiling area. The Swap command exchanges the numbers in Levels 1 and 2. It's above the right arrow key, here. But if there's no command line present, you don't need to press left shift. You can just press the right arrow key. Now you're ready to find the area of the square ceiling. Press left shift, x squared. Now add the 2 areas, plus. The 48 has lots of math commands you can use for your numeric calculations. This row of keys contains math commands, and the math menu has more math commands. They're all explained in your owner's manual. Just remember this rule. Enter the numbers for the command, then do the command. This is the same way you do a calculation on paper. Write the numbers down first, then do the math. So far, all of our numbers have been displayed in standard format. All of the necessary digits show. But no more. For certain problems, you may want numbers displayed with a different format. For money problems, you may want 2 decimal places, even if they're zeros. For other problems, you may want scientific notation, a mantissa between 1 and 10, and a power of 10, an exponent. Let's enter a few numbers so you can see how they're displayed. 4, enter. 0.0009, 1 over x. How about a number that's real small? You can use exponential form. 1.602 plus minus, enter exponent, plus minus 19, enter. That's minus 1.602 times 10 to the minus 19. Make a copy of this number, then find its inverse. Enter 1 over x. That should be enough. You can change the display format using the Modes menu. Left shift Modes. Right now, standard format is active. See the marker? You can change to 3 other formats: Fix, Scientific, and Engineering. Each of these needs a number to set the format, and you have to enter the number before you use the command. Here's what 2fix does. 2 decimal places. See how the numbers are rounded in the display? They're not rounded internally, though. Full precision is maintained. Okay, here's what 4sci does. A ones digit, 4 decimal places, and an exponent. The numbers are still rounded in the display. And now change back to standard format. All digits are shown, with no rounding in the display. Sometimes the stack will contain many entries, like it does now. There might be more entries or levels than show in the display. Well, you can see and edit the whole stack with the interactive stack. If you press up arrow, you get the interactive stack, assuming you're not doing something else that uses the up arrow key. Here's what happens. A pointer appears here, and the menu changes. You can't do normal operations now, but you can do things to the stack. The up and down arrows move the pointer. The display can scroll, so you can see any entry you want. You can use back arrow to delete an entry. You can use view in the menu to change an entry. On the next page, you can use drop n to drop the current entry and all entries below it. You can use keep to drop all entries above the current one. It's a good idea to get rid of old results you don't need anymore to save memory for other uses. Let's use drop n to drop all values except the area we found earlier. When you're done, press Attention to get back to the normal stack. If you want to save a result for later, you can leave it on the stack, but it's often more handy to store it in what's called a variable. A variable is like a register in other calculators, but it has 2 important differences. First, it can contain any kind of object, a number, an array, a program, whatever. Second, it has a name that you can give it, a combination of letters and other symbols. This lets you use descriptive names like these. But the name can't be the same as the name of a built-in command. Fix, for example, wouldn't be allowed. So store this result in a variable we'll call area. The number's already on the stack. Before you can store it, you have to enter the variable name. Remember, you enter the information first, then do the command. Because you want to use the name as just a name, not make the name do anything, you should enter it inside tick marks, like this. Tick, alpha, alpha, A, R, E, A. The tick mark means put this name on the stack. Before you press store to store the number, make sure the alpha enunciator's off, alpha, or else you'll just type another letter. Then store. See? The store command takes away the number in the name, and it stores the number in the variable. If the variable doesn't exist, store creates the variable too. To recall the number, you can evaluate the variable name, area. If you enter the name without tick marks, it's evaluated. That triggers the object stored there. For a number, you'll just get the number. Alpha, alpha, A, R, E, A, enter. The calculator also has a menu of variable names, called the var menu. It shows up when you press the var key. Here. Here's the area variable. You can use this menu to store and recall numbers. Let's subtract 24 square feet from the area to account for a door and window. 24 minus. Press left shift area to store the new number in area. You press the left shift and the menu key to store something in an existing variable. Press just the menu key to evaluate the variable name, to trigger the object stored there, to make the object do its thing. If it were a program, the program would run. For a number, you just get the value. You can use right shift and the menu key to recall the variable's contents, but for a number, you get the same result using the unshifted key. Get the new area. Area. If you're like me, you sometimes make mistakes using the calculator. Fortunately, my editor made sure mine didn't show up in this tape. Well, 3 shifted keys give you some ways of recovering from mistakes: last stack, last argument, and last command. The last stack key changes the stack back to its previous state, the way it was before the last command. The last arg key puts the arguments for the last command back on the stack. It doesn't drop anything from the stack, it just adds the arguments on. You still have the last result, and you have the arguments for further use. It's kind of like the last X key on earlier HP calculators, like the HP 41. The last command key restores the command line to its last state. It doesn't do anything to the stack. You can use this to correct your last command line, or to try it again with changes. If you press this key several times, you can recall any of the 4 most recent command lines. In this segment, we focused on numeric math with real numbers, but you can actually do math with other types of data: complex numbers, vectors, matrices, and numbers with units. Later in the tape, we'll cover these other numeric objects, but you can be assured the methods we covered here will still apply, because commands adapt to the type of data you're using. If you were going to solve a problem using algebra, you'd probably write out an equation or expression that describes the problem. Then you might solve for the unknown variable, and finally, to get a numeric answer, you'd plug in known values and find the value of the unknown variable. You might even try different sets of known values. Well, you can do all of this on the 48. We call it symbolic math. In many ways, symbolic math is like numeric math, except you can use algebraic objects instead of just numeric objects. An algebraic object is an equation or expression surrounded by 2 tick marks. The calculator strings it out on a single line, so a complicated expression might look a little awkward at first glance, but with a little experience, you'll catch on. To make things easier, you can use the equation writer application. It lets you see an algebraic object in a more common format, more like you'd see in a textbook. You can use the equation writer to create algebraic objects and to view and change them. Let's try some symbolic math. Enter the expression 3 minus x. Tick 3 minus alpha x, enter. Now multiply by 4 times. See, you can do math with algebraic objects, and the result is another algebraic object. Okay, let's simplify the result. Get the algebra menu, left shift algebra. Expand the expression to eliminate the parentheses. Expand. Then combine like terms to simplify the expression. Collect. For more complex expressions, you might have to use expand or collect more than once. Let's look at a savings account. This expression shows how much an amount grows to after n years of compound interest. You can enter this expression on the calculator in a form like this if you use the equation writer. First, start the equation writer, left shift equation. Now start the expression. Alpha m times, left shift parentheses, 1 plus alpha I, right arrow to get out of the parentheses, y to the x to start an exponent, alpha n, right arrow to get out of the exponent. See, the equation writer expression looks the way you'd normally write it. Now press enter to put the expression on the stack. See, it has tick marks. That means it's an algebraic object, and it's strung out in a linear form. If you study it, you can see it represents the original expression. Store this object in the variable bal for balance. Tick, alpha alpha, B-A-L, alpha, store. Now the variable bal shows up in the var menu, here. If you press bal, the expression stored there goes on the stack. That's what happens when an algebraic object is stored in the variable. If you press eval to evaluate the value of the expression, nothing seems to happen. Well, nothing else can happen because the variables m, I, and n have no values. They don't exist yet. Drop the expression from the stack for now. Now let's try creating those variables. Make the initial deposit $200. 200, enter, tick, alpha m, store. Make the annual interest rate 6%, 0.06, enter, tick, alpha I, store. Find the amount after 3 years, 3, enter, tick, alpha n, store. See, the new variables show up in the var menu. If you press bal now, the expression goes on the stack again, just like before. But if you press eval, you get a number. Variable names in the expression can be evaluated as numbers, so the expression can be evaluated. It gives the balance. So if you want a variable to be symbolic, not numeric, when you evaluate it, make sure it doesn't exist. On the other hand, if you want it to be numeric, store a value in the variable. You can also edit algebraic objects. Let's change the expression so that the interest rate is a percent rather than a decimal fraction. If you want to edit an object that's on the stack, you can press Edit. But our expression's in a variable, so we can use visit instead. Tick, bal, right shift, visit. See, the stack display goes away and you see only the object you're editing. Use the arrow keys to move around. The delete and back arrow keys, here, delete one character at a time. Okay, move the cursor to just after the I, like this, right arrow. Then divide I by 100. Divide 100. Press Enter to save the changed expression in the variable. Now let's find out what the balance would be at 6.5% interest. I already exists, so you can use left shift and the menu key to store the new value. 6.5 left shift I. Now get the expression, bal, and check to see what it looks like since we changed it. The down arrow key shows any object in its clearest form. For an algebraic object, that's the equation writer form. Okay, attention. Now find the balance at the new interest rate. Eval. So you can work with algebraic expressions without worrying about the numeric values of variables, and you can easily find values whenever you want. Now, consider the case of the unlucky gambler. He starts with a certain amount of money, pays a $5 entry fee, then loses half his money. Then he goes to another game, pays an entry fee, and loses half again. At this point, he has just enough money to pay his $1 bus fare home. How much did he start with? We don't have an equation for the problem, so let's create one. We could use numbers for the entry fee and bus fare, but let's use variable names instead, so we get a general equation. Call his starting cash balance C. Tick alpha C, enter. Subtract the first entry fee, E, tick alpha E, enter, minus. After his first loss, his cash balance is cut in half. 2, divide. Now subtract the next entry fee, tick alpha E, enter, minus. After his second loss, his cash balance is half again. 2, divide. This amount should equal the bus fare BF. Tick alpha B, alpha F, enter. Left shift equal. This equation describes the problem. We created it without even knowing what it was when we started. We just did symbolic math. C, his starting cash, appears in the equation only once, so you can use the isolate command to solve for C. Tick alpha C, left shift algebra, isolate. Okay, now store numbers in variables E and BF. 5, enter, tick, alpha E, store. 1, enter, tick, alpha B, alpha F, store. Now evaluate the equation, eval. He started with $19. Consider the motion of a pendulum. The frequency depends on the length of the pendulum and gravitational acceleration. You can write the equation using the equation writer. Left shift equation, alpha F, left shift equal, 1, divide, 2, left shift pi, right arrow, square root of x, alpha G, divide, alpha L. Press enter to put the equation on the stack. L appears in the equation only once, so use isolate to solve for L. Tick, alpha, L, isolate. Now you can use the define command to create a variable named L containing the expression on the right side of the equation. Left shift, define. Suppose for this calculation you'd rather give the period of a cycle instead of the frequency f. Well, you can substitute 1 over t for f. Just store 1 over t in f. Tick, 1, divide, alpha t, enter, tick, alpha f, store. Now get the expression for L from the var menu, var L. Press eval to evaluate the expression. See, the frequency term is replaced by 1 over t. If you assign values to g and t, you can find the length of the pendulum. 32.2, enter, tick alpha g store. Make the cycle 5 seconds long. 5, enter, tick, alpha t, store. Pi is a built-in symbolic constant, so its value is known. Okay, press eval to evaluate the expression. Notice that pi is still a symbol. That's because pi, and other built-in constants, aren't converted to numbers by eval. Sometimes you might want your answer in terms of pi. So now you have to do something that says, I want a number. That's the toNumber command, above the eval key. Right shift, toNumber. That's the length of the pendulum in feet. In this segment, we used isolate to find a variable in an equation. You can use quad for quadratic equations. You can use the rules application to rearrange equations in other ways. And your equations can get pretty sophisticated. You can even do symbolic differentiation and integration. Also in this segment, you saw how algebraic objects let you do symbolic math to get symbolic results and to get numeric results. Expressions and equations are also used by other problem-solving methods, as you'll see in the next few segments. The HP-Solve application is a handy way to solve an equation when you just want a numeric answer. If you use HP-Solve, you don't have to solve your equation symbolically. You can solve for any variable without changing the equation. In fact, you can find a numeric answer even when a symbolic solution isn't available. You define the problem using an equation, an algebraic object with an equal sign. Or you can use an expression, an algebraic object without an equal sign, or a program that returns a number. For an equation, HP-Solve tries to make the difference between the two sides equal to 0, so the equation balances. For an expression or program, it tries to make the value 0. It does this by trying possible answers over and over until it finds one that works, or until it can't get any closer. Let's look at the Doppler effect, where the frequency of a sound seems to shift because of the motions of the source and listener. We'll consider the case where the source and listener move along the same path. U is the speed of sound. Subscripts L and S refer to the listener and the source. Enter the equation using the equation writer, left shift equation. Alpha F, alpha L, left shift equal, up arrow, alpha U, plus, alpha V, alpha L, down arrow, alpha U, plus, alpha V, alpha S, right arrow, alpha F, alpha S. Put the equation on the stack. Enter. Now get the main HP-Solve menu, left shift solve. You want to use the new equation, so press New. You're prompted to give the new equation a name. Call it DOP, D-O-P. Enter. Now press the solver menu key to start the solver. Notice the solver menu has white labels for variable names. This helps you remember that these keys work differently from variable keys in the var menu. In the solver menu, the main function of the keys is to store values in variables, so you can set up the problem. The second function is to solve for a value. That's the left shift function. The third function is to recall a value. That's the right shift function. For comparison, in the var menu, the main function is the general idea of triggering the stored object, getting a value or expression, or running a program. The second function is to store a number or other object, the left shift function. The third function is to recall a number or other object, the right shift function. That's the same as for the solver menu. In our problem, suppose the listener isn't moving and the source is moving away at 65 miles per hour. What's the apparent frequency if the source frequency is 200 Hertz? 0, VL, 65, VS, 200, Fs. The speed of sound is about 741 miles per hour, 741 U. Press left shift FL to solve for the frequency the listener hears. About 184 Hertz. This message, 0, means you got an exact solution. The equation balances exactly. Several other messages are possible instead of 0. If you don't get 0, the equation doesn't balance exactly. You need to check how far it's off from balancing to decide if you got a valid solution. If you get a sign reversal message, the equation's unbalanced in opposite directions at infinitesimally close points. It usually means the equation balances between 2 points, and the calculator can't resolve points any finer. So the answer is a solution within the precision of the calculator. But it could mean the equation has a discontinuity there, not a solution. Now let's change the problem slightly. Suppose the listener starts moving, and now here's a frequency of 175 Hz. How fast is the listener moving? Enter the new information, 175 FL. Other values are the same as before. Solve for the velocity, left shift VL. The listener's moving away at almost 36 miles per hour. If instead the listener wants to hear 205 Hz, what velocity is required? 205 FL, left shift VL to find the new velocity. The listener should start overtaking the source at 85 miles per hour. You can check the current variable values using the review command, left shift review. This is a temporary display. It's a good way to see how your problem's set up. You can press attention to return to the stack. In this example, we could have used symbolic math to solve for each variable, but HPSolve makes it so much easier to find different combinations of values that satisfy the equation without having to change the algebraic object. Consider a field goal kicker. This equation shows how the height and distance of the trajectory depend on the velocity and angle of the kick. Let's analyze the situation. First, enter the equation, left shift equation, alpha y, left shift equal, alpha x, tan, alpha a, right arrow, minus, alpha g, divide, 2, right arrow, left shift parentheses, alpha x, divide, alpha v, cosine, alpha a, right arrow, right arrow, right arrow, y to the x, 2, enter. Now start HPSolve. Press New to use the new equation, then type a name, K-I-C-K, enter. Press Solver to start the solver. Okay, let's find the velocity required to get the ball over the crossbar from a distance of 40 yards if it's kicked at a 45-degree elevation. The crossbar is 10 feet high. That's why. The distance is 40 yards. 40 space 3 times to get feet. X. The angle is 45 degrees, A, and gravitational acceleration 32.2, G. Now solve for the velocity. Left shift V. This is the velocity in feet per second. The crossbar is above the ground, so let's see if there's a higher angle where the ball just clears the bar. If you just pressed left shift A, you'd find the same angle again. That's because the solver starts at the current value of A when it looks for a solution. In this case, that is a solution, so that's what you'd get. But it wouldn't be a different solution. So what you need to do is make A closer to another potential solution, a large angle like 70 degrees. 70, A. Now solve for A. Left shift A. This is the second angle where the ball just clears the crossbar. For both of the problems we solved, we created new equations and started HPSolve. If you want to solve an existing equation, you can pick it from the equation catalog. For example, go back to the Doppler equation you used earlier. Get the main HPSolve menu, left shift solve. From here you can see the equation catalog by pressing Cat. Use the arrow keys to move the pointer to the Doppler equation. Then press Solver to start solving that equation. The menu now corresponds to the Doppler equation, and the variable values are the ones you used before. In this segment, you saw how the HP-Solve application finds numeric solutions. All you have to do is make an equation and plug in values, and you get a message about the answer, because sometimes it's up to you to decide if the answer is a valid solution. You can use the Solver menu to enter values and find answers. You can even control which answers you get, and you can try different combinations of known and unknown variables without rearranging the equation. In the next segment, you'll see another problem-solving method that uses the same numerical technique used by HP-Solve. The plot application uses the calculator display as a tool for graphical analysis. You can plot functions just to see how they behave and get some approximate values, or you can pick certain features and solve for more precise numeric values. The most common type of graph is a plot of y as a function of x. That's the only kind we'll work with in this segment, but you can use plot to make polar plots of r versus theta, histograms, and other types of graphs. Because plots are based on numeric values, you can solve only numeric problems with plot. You can't get symbolic solutions. As with HP-Solve, you define the problem using an equation or expression, or you can use a program that returns a number. In fact, plot has several things in common with HP-Solve. You can enter your equation the same ways for both, such as picking from the equation catalog. Once you define an equation for one method, that's the equation used by the other method too, and they both use the same numerical technique to find solutions. Consider a radio broadcasting antenna. This equation gives the relative field intensity of the antenna as a function of antenna height and angle from vertical. The height is relative to the wavelength of the signal and is expressed as a fraction of 360 degrees. First, enter the equation, left shift equation. Alpha E, left shift equal, up arrow, cosine, alpha H, cosine, alpha right shift F for the theta symbol, right arrow, minus, cosine, alpha H, right arrow, left shift parentheses, 1, minus, cosine, alpha H, right arrow, sine, alpha right shift F, right arrow. Press enter to put the equation on the stack. We want to look at field intensity as a function of angle for a given antenna length, 6/10 of a wavelength for this problem. Store this value in H as a fraction of 360 degrees. 0.6, enter, 360 times, tick, alpha H, store. Now start the plot application, left shift plot. You have a new equation, so press New. Then type a name for the equation, A, N, T, enter. You're making a y versus x plot, so make sure the plot type is function. If you need to change the plot type, use p-type, here. Now press plotter to set up the plot. The display shows the plot type, the equation, and the independent variable. For this problem, you have to set the independent variable to theta. Tick, alpha right shift F, independent. The independent variable is now theta. The horizontal and vertical scales are always called x and y, no matter what the independent variable is. The angle can vary from straight up to straight down, from 0 to 180 degrees. 0, space, 180, x range. Instead of setting the vertical scale, plot the equation using auto-scaling. But first, clear the graphics memory, erase. Then plot the equation, auto. Auto first samples the equation to set the vertical scale, then plots the graph. If you want, you can plot points farther apart and either connect them or not. When the graph's finished, you can move the crosshair around the display with the arrow keys. Move it to a place near where the graph crosses the x-axis. If you press plus, you see the coordinates. It's around 48 degrees. Press plus again to turn off the coordinates. The crosshair moves faster that way. Let's find the precise angle that has 0 field intensity. Press Function to get the Function Analysis menu. The root key finds the nearest place where the graph crosses the x-axis. The crosshair is already near the point, so root. Plot uses the same technique to find the solution as HPSolve, so you should get the same answer either way. The crosshair moves to the point and the answer shows up. You can't see it right now, but the value goes on the stack too, so you can use it later. Okay, now let's find the angle and magnitude of the most negative field intensity. Move the crosshair near the point and press Extremum. The solution takes a little longer because the calculator first finds the derivative of the equation, then solves for where the derivative is 0. The coordinates of the point appear in parentheses. The first number is the horizontal value, the second is the vertical. The coordinates go on the stack too. The type of algebraic object you're using affects the type of graph you get. If you're plotting an expression, you get one curve of y versus x. If you're plotting an equation, you get either one or two curves, depending on your equation. Our equation is basically a definition. The left side is the single variable e, and the right side is an expression that defines e to be a certain function of h and theta. For this type of equation, you normally get one curve, for the expression on the right side. If the equation contains an expression on both sides, you get two curves, one for each expression. So the graph we've been working with so far is just a plot of the right side of our equation, an expression that returns a value for any combination of h and theta. Now let's find where the field intensity is greater than 0.5. If you want to find where an expression has a certain value, plot the left side of the equation too. If you set flag -30, the left side always gets plotted. So, attention, attention, 30, plus minus, right shift modes, next page, set flag. Then set e to 0.5. 0.5, tick, alpha e, store. Now replot the equation using the same scale. Right shift plot, erase, draw. This time you get two curves, one for the constant value of e and one for the expression, a function of theta. The points where they cross are the points where field intensity equals 0.5. To find the upper point, move the crosshair near the intersection and press Function Isect. Now move it to the other point and press Isect again. When you return to the stack, all the points you found are there. Attention, attention. The coordinates appear in parentheses. The first number is the angle, the second is the field intensity. This is the same as the format for complex number objects, so you can use the real, imaginary, and complex to real commands to extract components of the coordinates. To find the angular spread where the intensity is greater than 0.5, subtract the two coordinates. You're actually subtracting two complex numbers, minus. The angle is the real part of the complex number, so math, parts, real. That's the spread, almost 49 degrees. Now get the angle and intensity at the most negative point. First, swap levels 1 and 2. Right arrow. Then separate the coordinates into its two parts. Program, object, next page, complex to real. That's the field intensity and angle in levels 1 and 2. Before ending this example, clear flag -30. That's the default setting. Remember, we set it earlier so the left side of the equation would plot. 30, plus minus, right shift modes, next page, clear flag. The answers you get with plot are the same you'd get with HP-solve. The crosshair position for plot works the same way as a guess for HP-solve. You remember from the previous segment that with HP-solve, you easily input and find variable values, and you can solve for any variable at any time. But you don't see the behavior of the equation. Well, with plot, you see the behavior of the equation and can visually home in on solutions. But if you want to work with a different variable, you have to change the plot setup. So if you wanted to solve for h, the height of the antenna, you'd have to change the independent variable to h or rearrange the equation, depending on the problem. Of course, you can switch back and forth between plot and HP-solve. They both use the same equation. So it's just a matter of pressing right-shift plot or right-shift solve. That way you can use the advantages of both problem-solving methods. For certain problems, you may want to simply calculate a result from a formula using one or more known values. If you make a user-defined function, you can do your calculation in one operation. This makes it easy to repeat it for as many combinations of values as you want. If you do symbolic math, you may want to define a function that's not built into the 48. If you make a user-defined function, you can use it in the same way as a built-in function. So a user-defined function can simplify numeric and symbolic math. As you might expect from the name, function, it takes one or more values and returns one result. Let's look at the volume of a cone. For a known slant height and radius of the base, the volume is given by this equation. If you want to calculate the volume for various combinations of slant height and radius, you can make a user-defined function. Create an equation that shows the definition of the function. We'll name it cone. Left shift equation, alpha alpha, C-O-N-E, left shift parentheses, L, left shift comma, R, alpha, right arrow, left shift equal, left shift pi, times alpha r, y to the x, 2, right arrow, divide, 3, right arrow, square root of x, alpha L, y to the x, 2, right arrow, minus alpha r, y to the x, 2. Notice the left side of the equation names the function, cone, and defines the two arguments it needs. The right side shows how to use those arguments to get the result. The names you use for the variables in this definition aren't important because they're only used internally by the function. They're called local variables, and they have no relation to the global variables that show up in the var menu, even if their names happen to match. Press Enter to put the equation on the stack. Use the define function here to make a user-defined function from the equation. Left shift define. The function shows up in the var menu. If a cone has a radius of 4 centimeters and a slant height of 12 centimeters, what's the volume? Remember that the definition requires the slant height to be first, so 12, enter, 4, cone. What we get isn't the numeric result we hoped for, but if you press right shift to number, you get the number, 190 cubic centimeters. Because our function contains a symbolic constant, pi, the normal result is in terms of pi. If you always wanted to get numeric answers, you can change the calculator to not give symbolic answers. In the Modes menu, left shift Modes, Sim has a mark to show symbolic results mode. To get numeric results, press Sim. The marker for symbolic results turns off in the menu. In this mode, you'll get an error if you use a variable that's not defined because the expression can't be reduced to a number. Now let's try a 12 centimeter slant height and a 6 centimeter radius. Var 12 space 6 cone. This time you get a numeric answer right away. You can also use the function in algebraic form. Tick, cone, left shift parentheses, 12, left shift comma, 6, enter. You get the answer when you evaluate the expression, eval. Now change the calculator back to symbolic results. Left shift Modes, Sim. It seems reasonable that for any given slant height, there's a certain radius that gives maximum volume, and that this radius is always a certain fraction of the slant height. Let's find out what this fraction is. First, create an expression for the problem. Tick, var, cone, left shift parentheses, alpha s, left shift comma, alpha f, times alpha s. Enter. The radius is a fraction of the slant height, and f is the fraction you want to check out. The plot application can show how the volume is affected by the fraction f, but it's a numeric method, so you have to assign a value to s. Because s won't change the overall behavior, make s 1. 1, tick, alpha s, store. Now start plot, left shift plot. You want to plot the expression on the stack, so press New and name the equation vcon. Then press Plotter to set up the plot. Reset the plotting parameters, next page, reset, next, next. Make f the independent variable, tick, alpha f independent. The fraction f should vary from 0 to 1. 0, space, 1, x range. Now plot the graph using auto-scaling. Erase, auto. To find the place where the volume is highest, move the crosshair near the maximum. And press Function Extremum. To find the maximum, plot has to differentiate the equation, meaning it has to find a symbolic derivative of the user-defined function. The fact that we get an answer shows you can differentiate user-defined functions. Attention, attention. The peak volume occurs when the radius is about 82% of the slant height. There are certain limitations to user-defined functions. For example, there's no inverse function defined, so you can't use symbolic math to isolate a variable that's an argument. But user-defined functions provide a simple way to add new functions to the 48 without having to think about programs. In the next segment, we'll look at solving problems by creating programs. Programs are the ultimate problem-solving tool on the 48. If you can't solve a problem with the other problem-solving methods, even with a combination of those methods, you may be able to make a program that'll solve it. Other methods have limitations that restrict the types of problems they'll solve, but in a program you have access to all of the calculator's capabilities, so you can use whatever operations get the results you need. Now, maybe you've programmed a computer or calculator before. If so, you may think of line numbers and labels. Well, a program on the 48 is just a series of objects that are processed in order. No line numbers or labels. And you can add conditional structures to guide the process. The objects you'll see in programs are the same ones we've been using. Commands, numbers, variable names, expressions, user-defined functions. There's nothing really special about how you make a program. You create it in the command line, just like you created other objects. To start, let's look at some simple programs. A program is marked by French quote delimiters. We call them program quotes. So that's how you start making a program. Left shift program quotes. There's no special program mode as for earlier HP calculators like the HP 41. Now let's put in a couple of numeric objects. 1, space, 2. Press Enter to put the program on the stack. Like other objects, a program takes up only one level on the stack. Let's make another copy to look at later. Enter. Now press Eval to evaluate the program, to run the program, to process each object in the program. See, the program's taken from the stack, and the two numeric objects are processed. They're put on the stack. Try a program that includes commands. Left shift program quotes. Instead of being executed, commands go into the program. 1, plus, left shift, x squared, enter, enter. This program uses a number from the stack, so enter a number, 6, enter, then bring the program back to level 1, swap. The program will add 1 to the number and square the result, eval. Now try a program that uses an algebraic object. Left shift program quotes, tick, alpha q, right arrow, store, tick, alpha q, plus, 1, divide, alpha q, right arrow, right shift to number, enter, enter. This program uses a number from the stack, so enter a number, 8, enter, then bring the program back to level 1, swap. The program will create variable q using the number on the stack. Put the expression on the stack and convert the expression to a number, eval. Suppose you want to calculate the volumes of several cylindrical oil storage tanks. For each tank, you know the height and diameter. Let's create a program to do this. If you start with the height and diameter on the stack in that order, make a program object that includes the steps for finding the volume. Left shift program quotes. Now, perform the same operations you'd use to make the calculation using simple numeric math. Square the diameter that's on the stack, left shift x squared. Multiply that by the height, it's already on the stack too, times, enter pi and multiply, enter 4 and divide. The result should be the volume of the tank, but pi is a symbolic constant, as we saw earlier. To get a numeric answer, you need to include right shift to number. Press enter to put it on the stack. Store the program in a variable named vtank, tick, alpha alpha, v, t, a, n, k, alpha, store. vtank shows up in the var menu, though the whole name doesn't fit in the label. To use the program, put the height and diameter of a tank on the stack, then press vtank to run the program. Let's use a height of 50 feet and a diameter of 80 feet. 50, enter, 80, vtank. That's the volume in cubic feet. When you pressed vtank, the program stored there was triggered. It ran. In this program, we did our calculations by putting numbers on the stack and operating on them. But sometimes it's easier to use symbolic expressions for your calculations. For one thing, it's easier to interpret your program. And if your calculations aren't simple, keeping track of the objects on the stack can get pretty tedious. So let's replace the program with one that uses a symbolic expression. But let's do it in a way that doesn't clutter up the var menu. You can do this by using local variables. Local variables exist only while the related calculation is happening. Then they go away. You'll see how this works in just a second. Start the new program, left shift program quotes. To use local variables, you have to name them and define an expression or program they're used in. Use the arrow command, here, to start naming the variables. Right shift arrow. You can use any names for local variables, but a common convention is to use lowercase names for local variables, to distinguish them from global variables, the ones in the var menu. Use H and D. Alpha left shift H, space, alpha left shift D. Now enter an expression for the volume, space, tick, left shift pi, times, alpha left shift H, times, alpha left shift D, y to the x, 2, divide, 4. Arrow HD takes two values off the stack and stores them in H and D. The expression pi HD squared over 4 is the only part of the program that can use H and D. Those variables don't exist outside that calculation. When you run the program, the local variable expression is evaluated. But pi is a symbolic constant, so include toNumber to get a number. If you don't want the line to get too wide for the display, you can enter a new line character first. Line breaks don't matter in a program. Right arrow, right shift new line, right shift toNumber. Now put the program on the stack. This program's equivalent to the earlier version, but it looks pretty different. Store this version in vtank, left shift vtank. Then repeat the earlier calculation, 50, space, 80, vtank. Now let's change the program so you can enter the numbers in either order. Assume you know the diameter is always larger than the height. Make a program that takes any two numbers and puts them in order, minimum, maximum. Left shift program quotes, math, parts, next page. See, nothing goes into the program when you change menus because the keys you use don't correspond to objects. They're just keyboard operations. Okay, use min to get the minimum of the two numbers on the stack. The numbers that were on the stack are replaced by the minimum, so you have to get the two numbers back. You can do this with last arg, right shift last arg. Then get the maximum, max. Notice that this program will return two results. Store the program in a variable named min-max. Enter tick alpha alpha m-i-n-m-a-x alpha store var. Now edit vtank to include this program. You can use the visit command to edit the contents of a variable. Tick vtank right shift visit. In the program, you want to adjust the positions of the numbers before you start the calculation. So move the cursor to the start of the first command, right arrow. Now insert the name of the min-max program, var min-max. Press enter to keep the change. Now, when you press vtank, the name min-max is evaluated as part of the process, meaning the program stored there runs. Repeat the previous calculation with the numbers reversed, 80, space, 50, vtank. You get the same answer as before. Your program may have to use branching. Branching lets you skip over certain parts of the program or execute certain parts more than once. Branching is defined by conditional structures in the program. We don't have time to go into all of the details of conditional structures, but we can look at some examples. This program uses the if-then-else-end structure to give you two branching choices. It takes a value from the stack and tests it. If it's less than or equal to 0, it executes the program stored in too small. Otherwise, it puts x on the stack and calculates its logarithm. The program skips over the part that's not needed. If-then-else replaces the goto command of earlier HP calculators, like the HP41. This program uses the case-end structure to give you several branching choices. It takes a value from the stack and compares it with two choices. It either executes the program stored in option 1 or option 2, or it puts the string bad option on the stack. This program uses the for-next structure to repeat part of the program a certain number of times. It uses 1 and a number from the stack as the range of counter values. The first x just names x as the local counting variable. The program puts each 1 over x squared term into the list of terms. A list is especially handy for inputting or outputting several numbers or other objects in a compact form. This program uses the while repeat end structure to repeat part of the program an unspecified number of times. As long as the depth of the stack is greater than 1, it adds the number in level 2 to the sum in level 1. If the stack starts with less than 2 numbers, the addition never happens. If you or other people will use your program many times, you can include input prompting and output labeling. Look at this example. The prompt command prompts for input with a string and halts execution. After you enter two numbers and press left-shift continue, the program calculates the area and marks it with a tag, area, so it's easy to interpret. Continue replaces the run-stop key of earlier HP calculators, like the HP41. You may have noticed that all of the programs you've seen here start executing at the begin program quotes and don't finish until the end quotes. This may not seem too unusual, but many other calculators, like the HP41, let a program have several entry points and several exit points. Not so with the 48. The 48 uses what's called structured programming, meaning programs have simple, predictable organization. It's designed to simplify programming by letting you make smaller, building block programs that you can call from higher level programs. The min-max program we used earlier was a building block for the vtank program. If this makes programming seem too tricky, remember, you can still make regular one-level programs. Well, we've only scratched the surface of what you can do in a program. Your owner's manual has lots more information, plus some sample programs. You'll find programming a powerful tool for solving problems. At this point, we've tried the 6 problem-solving methods we listed earlier. There's certainly more to each of the methods than we covered here, but at least you've seen the basic operation. Well, the 48 can do other things to help make it even more useful. We'll look at some of these in the next few segments. So far, the only numeric data we've worked with has been real numbers. For many calculators, that's the only kind you can get. Well, the 48 works with other kinds of data, other kinds of objects, as we mentioned earlier in this tape. And, as we've seen, the commands you use adapt to the types of objects you're using. You don't have to do anything special to calculate with different kinds of data. So let's look at some different kinds of numeric data you can use. In this segment, we'll try out complex numbers, vectors, and matrices. Suppose you take the square root of -9, or the arcsine of 2. The result of either of these calculations is not a real number. So let's see how the 48 shows the results. 9 plus minus square root 2 left shift arcsine. Both answers are actually complex numbers, represented by the calculator as a pair of numbers inside parentheses. The first number is the real part, and the second number is the imaginary part. Complex numbers represent points in the complex plane. They're usually represented by rectangular coordinates, a real value and an imaginary value, an x value and a y value. For some problems, you may want to show the complex number as a magnitude and angle. Just change the calculator to one of its polar modes, right-shift polar. Now all of the complex numbers show up as an amplitude and an angle, complete with an angle symbol. The R-angle enunciator, here, turns on to indicate polar mode. To enter complex numbers, use the parentheses delimiters. Let's enter the number 5 at an angle of 20 degrees. Left-shift parentheses, 5, right-shift angle, 20, enter. Now enter 4 plus I8. Left-shift parentheses, 4, space, 8, enter. Both numbers are displayed in polar mode. To see the real and imaginary parts, press right-shift polar to go back to rectangular mode. Most of the math keys work with complex numbers. The Math Parts menu contains other commands related to complex numbers. Absolute gives the magnitude of a complex number. Arg gives the polar angle of a number. Okay, now let's look at vectors. The most common vectors are 2- and 3-dimensional vectors, but vectors can really have any size. A vector consists of a pair of square brackets containing a series of numbers. Here's a few examples. Left shift brackets 1 space 2.5 space 0 space 7 enter. How about a 3D vector? Left shift brackets 10 space 10 space 10 enter. And a 2D vector 3 space 4 left shift 2D. The 2D and 3D commands here take 2 or 3 numbers and make a vector. 2D and 3D vectors are displayed according to the coordinate mode you're using. Right now we're using rectangular mode, so you see each component as an amount, an amplitude. Change to cylindrical mode, math, vector, R angle Z. You can make the values easier to see by changing the display format. Left shift modes, 1, fix. Now change to spherical mode. Right shift last menu, R angle angle. The 3D vector changes, but not the 2D vector. Cylindrical and spherical modes are both polar modes, so 2D vectors appear the same in those modes. The 4D vector isn't affected by the coordinate mode at all. A matrix is an array of numbers in rows and columns. For comparison, a vector is an array of numbers with just one column. It's an n by 1 matrix. The easiest way to enter a matrix is using the matrix writer application. You start it by pressing right shift matrix, like this. Then you enter the numbers in their places. 3, enter, 2, space, 1, enter. Press down arrow to start a new row. You can do calculations in your entries too. 2, square root, enter. Left shift pi, right shift 2 number, enter. The current size of the matrix shows in the top corner, here, 2 rows by 3 columns. Press enter to put the matrix on the stack. The calculator uses nested square brackets to show the structure of the matrix. The outer brackets mean it's an array, just like for vectors, and the inner sets of brackets group the numbers into rows. Let's store this matrix in a variable. Tick alpha m, alpha a, store. You can store and recall individual elements in a matrix without having to put the entire matrix on the stack. Recall the element at row 2, column 1. You have to specify the matrix and the element number. Tick var ma, enter, left shift brace 2 space 1, that's the row and column numbers in a list, enter, program, objects, left shift previous, get. You can use plus, minus, times, and divide with vectors and matrices, and 1 over x with square matrices. Some special matrix operations are included in the Math Matrix menu. For example, we can transpose the MA matrix without putting it on the stack. Tick var MA Math Matrix Transpose. We mentioned earlier in the tape that you can use the down arrow key to view or edit an object using its specialized editor, the matrix writer for a vector or matrix. If the object's stored in a variable instead of on the stack, you can use right shift down arrow, tick var MA, right shift down arrow. See, now the transposed matrix is 3 rows by 2 columns. Attention. Finally, we'll go back to standard display mode, left shift modes, standard, and rectangular mode, right shift polar. You can also have complex vectors and matrices. All you have to do is put complex numbers in all of the cells. So, for example, you could use complex matrices to solve simultaneous equations having complex coefficients, such as for an electrical circuit. In addition to real numbers, complex numbers, vectors, and matrices, there's another kind of number you can use on the 48. We'll look at that in the next segment. You've seen how the 48 works with different kinds of numeric quantities, real and complex numbers, vectors, and matrices. Well, let's look at another variation, real numbers with measurement units attached. They're called unit objects. The value 45 conveys a certain amount of information. The value 45 miles per hour conveys additional information. It has a number and units. So 45 miles per hour means something different from 45 feet per second. And you can put this difference to work in several ways. You can simply combine values with their units to make them more meaningful. You can convert a value with units to a value with different units, and you can calculate with unit objects and let the calculator automatically convert the units. The calculator gives you lots of built-in units. They're split into 16 classes. The Units menu lists these 16 menus, and these menus contain the individual units that are available, over 120 of them. Also, you can combine the built-in units to make more complicated units, like acceleration, feet per second per second. So whatever units you want, they're probably available. And if you don't find the units you need, you can invent your own. Okay, the first person to officially run 100 yards in less than 10 seconds was John Owen. He did it in 9.8 seconds in 1890. I wonder what his average speed was in miles per hour. That should be easy to figure out. Get the Units menu, left shift Units, then get the Length menu, here. He ran 100 yards, so press 100 yards. See how the underscore joins the number in the units? He ran this distance in 9.8 seconds. Get the Units menu again, left shift Units, then get the Time menu. Now enter the time, 9.8 seconds. Divide the distance by the time to get the speed. It's in yards per second. The numbers divide and the units divide. Miles per hour is a built-in unit of speed. It's in the Speed menu. So left shift Units, Speed. To convert to a standard unit, just press left shift and the menu key, left shift MPH. He averaged over 20.8 miles per hour. You can also convert to any other units, say inches per second for this example. First, create any number with those units, like 1 inch per second. So press 1, then get the Length menu, left shift Units, Length, and press inch. Now get the Time menu, left shift Units, Time. To divide by a unit, press right shift and the menu key. So right shift seconds. See, it puts seconds in the denominator of the units. Well, the original value is in level 2 and the desired units are in level 1. So it's time for the convert command. Convert is in the right shift units menu, unit operations. Convert. His average speed was over 367 inches per second. Let's look at two other commands in this menu. UBase converts a value so it has base units, units from the International System, so-called SI units. So if you press UBase, you get the speed in meters per second. UVal gives the numeric value of the quantity. It changes a unit object into a real number. So if you press UVal, the units disappear. Now let's see how the calculator automatically converts units. Suppose the relative pressure inside a pressurized tank is 1,475 pounds per square inch. You want to find the absolute pressure in the tank. To do this, you have to add the atmospheric pressure to the relative pressure. Look at the pressure units menu. Left shift units, next page, pressure. Well, you can enter the atmospheric pressure as 1 atmosphere, 1 atmosphere. Now enter the relative pressure, 1,475 psi. To add them, just press plus. That's the absolute pressure in psi. The units are automatically adjusted to the units that are in level 1. So all you have to do is make sure the units you want are in level 1. Automatic unit conversion is really handy for HPSolve. You can add units to each variable value, and any conversions that are needed are done automatically. Let's look at the centripetal force that keeps a car in a circular path. The centripetal force depends on the mass of the object, its speed, and the radius of the turn. What's the force on a 2-ton car going around a 100-foot radius curve at 25 miles per hour? First, enter the equation. We'll use the equation writer. Left shift equation, alpha F, left shift equal, alpha M, times, alpha V, y to the x, 2, right arrow, divide, alpha R. Enter the equation, then start HPSolve, left shift solve. It's a new equation, new. Name it C, E, N, enter. Okay, use the Units menu to enter the values with units. Left shift units, mass, next page, 2 tons. Left shift units speed, 25 miles per hour. Left shift units length, 100 feet. Even though you're solving for the force, it needs to have units for the equation to balance. This also gives you the chance to decide what units you want. Pounds for this example. If you don't have a guess for the force, you can use 0 pounds. So, left shift units, next page, force, 0 pounds force. That gives us a pretty incompatible set of units, but it shouldn't be any trouble for the 48. Okay, now get the solver menu. Right shift solve. Store the values F, R, V, and M. Now you can solve for the centripetal force. Left shift F. The units are automatically converted during the calculations. The result is 1,671 pounds force. Now let's find the speed that gives a force of 3,000 pounds. 3,000 F. See, we didn't enter any units. The units from before, pounds, are automatically used unless you enter different units. Solve for V. Left shift V. The speed is about 33 miles per hour. Remember, you use units with real numbers to form unit objects. You can't use units with complex numbers, vectors, or matrices, but you can put unit objects in a list. You might do this if you were making guesses for HPSolve. Certain applications restrict the use of unit objects, such as plotting and statistics. You can get an idea of just how powerful units can be from these examples. By including units in your calculations, you eliminate the need to check units separately and to figure out conversion factors. It can add a whole new dimension to your calculations. To help keep in touch with the real world, the 48 has the time application. You can use it to get the time and date, to set alarms, and to do time and date arithmetic. Start the time application by pressing left-shift time. The date and time appear in the upper corner of the display. Even though the values may be wrong, you can set the date and time formats, the ways the values are displayed. Press the Set Menu key to get the Setup menu. If the date has slashes, like this one, the numbers represent the month, day, and year. The MD key changes the format to day, month, year, with period separators. We'll use month, day, year. If the time has an A or P at the end, like this one, the time is in 12-hour format, with AM or PM added. The 1224 key changes the format to 24-hour format, with no AM or PM added. We'll use 12-hour format. Now let's set the date and time. Today's date is July 18th, 7/18/1991. So type the date like this, 7.18/1991. Then press To Date. It's 3:45 p.m., so type the time like this, 3.45, then press To Time. Press AM/PM to change the time to PM. When we change from daylight time to standard time, it's easy to adjust the time. Left-shift time, adjust, hour plus, hour minus, to change back. You can make finer adjustments to the time in the same way. Normally, the time is visible just when you get the time menu. If you want, you can make it visible all the time. Left-shift modes. See, the time disappears. Next page, clock. Now the time shows up in the status area. Press clock again to turn it off. Okay, now let's see how to use the alarm. Set an alarm for 3:49, just a few minutes from now. Left-shift time, alarm. Enter the time, 3.49, time, AM/PM. Today's date is already assumed, but you can set it just like you set the alarm time. You can also define an action that happens at the alarm time. Usually, you just type a message that's displayed. Create a string containing a message. Right-shift quotes, alpha alpha, T, left-shift alpha to lock lowercase, time to stop. Alpha, execute. Now press Set to make the alarm active. You can also make alarms repeat periodically. Suppose you have a tennis lesson at 6:30 every Friday evening. Let's set a repeating alarm at 6:15 as a reminder, starting tomorrow. Alarm, 7.19, to date, 6.15, to time, AM/PM. Right-shift quotes, alpha alpha, T, left-shift alpha, tennis lesson. Alpha, execute, repeat, 1, week, set, attention. Instead of using a string as the object to execute, you could use some other object, like a variable name. No message is displayed at the alarm time, but the object is evaluated, so you can make any kind of action happen. There's the alarm we set earlier. It says time to stop. If you press any key while it's still beeping, you stop the beeping, but you also acknowledge the alarm, which deletes it. We didn't press a key, so the alert annunciator, here, means we have an alarm that's not acknowledged. Press left-shift time to see the message. After you read it, you can acknowledge the alarm. Acknowledge, attention. You may find the time and alarm operations handy for everyday use. Plus, you can use time and alarm commands in programs. In this tape, you've seen quite a bit about what the 48 can do, and you can be sure there's a lot more you can do with it. Here's some other features you might find handy for solving problems. Changeable operating modes let you control the calculator's behavior. The behavior is controlled by flags stored in memory, 64 of them. Basically, each flag controls a particular behavior. An appendix in your owner's manual lists all of the flags, but for the most common changes, you can set the behavior in the Modes menu, like we did earlier. The Custom menu and the User keyboard let you put operations in a menu or on the keyboard. You can put the commands, programs, and other objects you use most often in places that are most handy. Directories can help simplify how you use the calculator. A directory represents a completely separate part of memory, containing an independent collection of variables. When you first get your calculator, it contains one directory, named Home. You can create other directories to organize your variables into logical groups. Statistics commands let you analyze and plot single sample and paired sample data. Graphics commands let you draw and label pictures in the display. Infrared serial input-output lets you print information on an infrared printer, or send information between two calculators, or with an optional interface kit, exchange data with a PC or Macintosh computer. Plug-in RAM cards give the 48SX model more memory for storing variables or making backup copies of important information. You can add up to 256,000 bytes of memory. You can also remove a card containing information, and you can use that information later when you reinstall the card. Plug-in application cards expand the capabilities of the 48SX model. For example, the HP Solve equation library card gives you immediate access to more than 100 sets of equations for common scientific problems. It also contains a periodic table, financial equations, and a game. We'll turn off the calculator and install one of these cards now. Let's take a quick peek at the periodic table. Left-shift Library, Periodic Table Menu, Periodic Table Application. That's a picture of the periodic table. For any element, you can get any of 25 properties, like density and thermal conductivity. Well, we can't cover everything about the HP48 in this tape, but what we have covered should give you a good start towards using the calculator to solve your problems. Look in your owner's manual to find out more about the features that interest you most. If you want, you can rewind this tape to any segment and watch it again. You might pick up a few details you overlooked previously. We've looked at many ways to use the power of the 48. I'll finish by showing you one more thing you can try.